Okay, so what is functional programming? Well, first you have to know other types of programming. So you see, we had this the very basic coding in Python that we didn't talk about what type of programming it is. Those are called either imperative, or it's also known as procedural programming. And I guess they have slightly different meanings. I don't know exactly the difference. But it's basically programming that we are used to. Like you make the for loops do this. Basically, imperative programming is telling the computer do this, do this, do this, do this, and at the end of the day, you have something. Okay. Then we also learned a slightly different type of programming. Do you remember what it was? Something called OOP. OOP stands for Object-Oriented Programming. Yes, Object-Oriented Programming. This basically takes the data very close to the functions. Functions inside an object is called a method, and objects have their own variables, and therefore you don't have to think about which function should be applied to this type of data. It's just a single object, so you just have that object, just tweak the data inside the object and just execute the method, and everything's good. So that causes a lot less confusion when you're programming. Now, in the old days, when we didn't have object-oriented programming, it's like C, even adding two functions had many different names. Like there was addition for integers, addition for floating points, addition for double floating points. So it's a lot more complicated if you don't have these object-oriented programming. Well, there are other ways to go around it, but object-oriented programming makes the data become close to the methods. And then it also has other nice things, right? Abstraction and encapsulation, inheritance. So it organizes the program very nicely. However, once people started using object-oriented programming, there were a few problems in the field. Notably, inheritance, which is like having another object as a close copy of the previous object, but you tweak something to make a new object. Those, if you make new classes out of inheritance, debugging was really hard because you didn't know where the function was defined. You had to go back and forth searching for this one function. And imagine when your program has double inheritance. It's like you have a class which is an inheritance of another inheritance. That becomes even harder. So debugging was a big issue. Computer scientists started to think about how to make programming more error-proof. And they took hint from mathematics. And when they looked at mathematics and see how mathematicians made sure that their arguments were foolproof, they realized that there were some things that mathematicians made, especially there were some logicians, earlier work by some logician named Churchill and then later by Curry. These people made some logic systems that were very good, very easy to see that it's foolproof. There is no error. So computer scientists took that idea and started writing these something called functional programming. Now, the functional programming that these computer scientists pushed for is a bit different than the ones that are used now. For example, they wanted to make functions only take a single value and spit out a single value. That seemed to be a big limitation. So let's try to think about that point a little bit. So first, here's a function, add two numbers, x comma y. All right. And then what it does is it returns x plus y. A simple add function. Yeah. I mean, nobody would be using this function. It's way easier to just actually add things. Yeah. But let's just say you made a function that does something like add. It takes two things and combines them in some way. Now, how are you going to make this so that it takes in only one value? That's a bit crazy, right? I mean, how can you add if you can only accept one value? Right? So that seems like a very big limitation, but computer scientists were able to learn from the logicians that there is something called currying. Currying is a way to build a bigger function from a smaller one by allowing functions to be returned. Okay, so here's a more functional kind of way to make the same function, which is to say define add num, okay, and then if it has x, right, then what you do is you define a new function, define add 2 or something like that, right, of y, and then that function returns x plus y. So it's a new function that adds two numbers, right? And then what it does is it returns the add2 function back. Okay. Notice that I didn't put opening and closing parentheses to add2. It means that I'm not executing this function. I'm just returning the function itself. Okay? So this is somewhat weird, but it works. So see, add num. So let me compare the two. If I do add 2 and 3, it gives you 5, of course. But if I do add num of 2, it returns some kind of a function that's named add2. Okay, and it's under this. Right now, the main loop is running, and then there's the add num function, and inside the add num function, there's the add2 function defined, and that's being returned. How do you use this? Well, you do add num of 2 and then 3, and you get 5. You get the same result. Okay, and if you think about it, both add num and add2 are functions that take in single value and returns a single value. Does it make sense? Right? Takes in a single value x and returns a function which is single thing, right? But that function is, because it's a function, it takes in one thing and returns something else. Okay, so that's like the basic idea of currying. This is an example of what's called currying. Okay, so at this point you might think, well, this is totally useless. Who would program like this? It just made a 2-line code into multi-line code, and even execution is much harder. Right? But that's the basics of functional programming. It's a common misunderstanding to think, if somebody says, oh, I like to do functional programming, and people who don't know about what functional programming is, they think, oh, you like to use functions. But that's a big mistake. Okay. Functional programming, a priori, is about being able to send in functions as an argument of a function. You can send a function to a function, and you can return a function as a return value. Now, the early programming languages didn't have such a concept. So if you're programming in the early days of Fortran, COBOL, probably haven't heard of these languages, but these were like ancient languages where people used because it was a lot more convenient than writing machine code. But these programming languages didn't have the capabilities of sending in functions and returning functions. Okay. All right. So what is the big draw for this? So now I have to sell this, although it looks really complicated. The big idea in functional programming is pure functions. Now, what are pure functions? Pure functions are functions that take in values. So nowadays, you really don't have this limitation that functions should have only one value. But still, a lot of times, people who write in functional programming style would do something like currying because it allows people to build simple functions, build complicated functions from simple functions. You can reuse functions. That's the idea. But the more important part is, let me go back to pure functions. Pure functions are functions that are like the mathematical functions. Functions where it takes an input and it gives you an output, and the output is only dependent on the input. Okay? And in addition, so output only depends on input. That's one thing. Okay. Another property is that the output is the only thing the function does. Just like mathematical functions, right? So we had some functions before as an example where the function would print something, right? That's a big no-no because print is sending information to the console to show something, right? That's not allowed in pure functions, okay? Pure functions cannot read database because let's say you have a function which looks at today's weather and tells you what the weather is, okay? Such a function cannot be a pure function. Because it doesn't depend on what you've sent in. It just looks up the database by looking up somewhere, okay? So pure functions, in other words, no side effects are allowed. So you can't modify global variables. You can't read from the database. You can't write to database. You can't print anything. The only thing it's allowed to do is return something. That's a very strong restriction. You know? And often, if you're programming in functional style for the first time, this becomes like a big shackle that it's hard. You want to get freed from it. You don't see the point. But if you write a big program using only pure functions, and maybe later you collect the output and print it somewhere or do something, right? Then you can be sure that everything that you wrote is not doing something crazy. See, the worst kind of programming would be where you have some kind of a global variable where a lot of the functions would behave according to the global variable, but not only that, that global variable will be changed by several functions in the program. Then when you see an error, it becomes really impossible to track down the error because you don't know which one just changed that global variable to something else that you didn't want. Yeah. So as opposed to that, because pure functions do not have any side effects, then you can be sure of what this function is doing is exactly what you see. Okay? Functions with side effects, you never know what's in there. You have to dig deep to make sure that it's not doing something funky. Functions that are pure, you can have peace of mind. Okay? So one rule of thumb to figure out if a function is pure or not is if you can replace the input and output. So maybe I should do something. There's something. Okay, so rule of thumb for finding out if your function is pure is if you can memoize So another nice thing about pure functions is because the output only depends on the input, if you have seen that input before and the pure function did compute it, then you can just memo the input and output pairs, and then you don't have to use that again. Okay, so that's called memoization. So let me give you an example of a memoization. Okay, so first thing is here's a Fibonacci sequence. Do you know what a Fibonacci sequence is? Like the first number is 1, right? And then the next number is also 1. But then the next number is 1 plus 1, which is 2. And the next number is 1 plus 2, which is 3. And then the next number is 2 plus 3, which is 5. What's the next number? 8, right? And then so on and so on. Okay, so this is what's known as the Fibonacci sequence. Okay, how do you implement this as a function? Well, let's say we have a function that gives you nth Fibonacci sequence. Okay, so let's see. Define fib n. Okay, and I'm going to say if it's 0 or 1, return 1. Right? That's 0 or 1. If n is the 0th Fibonacci sequence is 1, the first Fibonacci sequence is 1. We're going by the Python convention that the list starts from the 0. Okay, so we're going to say if n is, we're just going to assume that n is always non-negative, so we'll just say non-negative integer, okay? So if n is 1 or less, then just return 1, okay? All right, but now what you do is your nth value is the sum of, see, if this is nth value, this 5 is obtained by n minus 1th value and n minus 2th values, the 1 before and 2 before. So what I'm going to do is return Fibonacci of n minus 1 plus Fibonacci of n minus 2. Okay. Now let's see how this one works. Fibonacci of 0 is 1, 1 is 1, 2 is 2, that's good. 3 is 3. Okay, 4 is 5. Yeah, so it's just calling itself. So I've shown you such an example in quicksort, right? So you can have a recursive function. And if you think about it, recursive functions are composition of functions. So it's very much in the philosophy of functional programming. Functional programming is all about composing functions, which this is doing. Okay, so you have this, but now this becomes slower as you put in bigger numbers. So if I want the 100th Fibonacci number, then it'll have to call itself 100 times. But every time you call itself, it's like you're doubling your Fibonacci things, right? So if you call itself, it's going to wait a little bit, actually quite a lot. This is basically unusable, right? It's just too long. However, this is a pure function because you know that this does not rely on external data, right? The output of this value would depend on the n, right? So what we can do is we can speed up this by memoizing this. See, if I already called Fibonacci of 4 at some point, there's no point in calling Fibonacci 4 again. So you can save on that. So let's Control C. I don't think this is going to finish. All right, it's calling like, yeah. All right, I'm surprised that it didn't give me any overflow error, stack overflow. Okay, so now what we're going to do is we're going to memoize this function. I'm going to define a wrapper or a memoize function. So memoize. Okay, and the memoize function will receive a function to memorize. Okay, and we're going to define the known values. So initially, I don't know anything about this function, but what I'm going to do is, so what we're going to do is we're going to make the memoize function to return a new function. So we're going to define a new function to memoize a new func of it's going to get n. Okay? And what we do is if n is in the known, one of the key values in the known, then instead of running the function that's given to us, we're just going to return the value of the known output for the input n. On the other hand, what we are going to do is else, we're going to say that output is you apply the function to this n that we just received, and then we're going to record that. So we're going to say known n would have the output value. Okay, and then what we are going to do is once all this is done, you're going to return the new function itself. Okay. All right, so now let's see how this thing works. We now have a memoized version of the Fibonacci. So we have memoize. So you see the logic here. If it sees some input that the memoize function never have seen, what it does is it takes the output of the function and records it in the dictionary. So no, sorry, I just realized there's a typo here. Should be known. Okay. So the output and the input pair is stored in the dictionary as a key value pair. So next time when the same n is questioned, instead of running the function, it will just return the known output value. That's the beauty of this. Okay, so what I'm going to do is I'm going to say fib2 is now the memoized version of the original fib function. Sorry, I also made another spelling mistake here. It should be new_func. Okay. All right, so let me do that again. Okay, now fib2 is the memoized version of the original fib. And let's see how it does 100. I guess it's still suffering. Okay, so I should really have done this. In the definition for fib, where's the definition for fib? Yeah, the problem is when I'm calling myself, this is the problem. I'm calling the old fib. Right? This one's not the memoized version. So the correct way to wrap this around is not to name fib2 as fib, but you have to overwrite fib entirely. So what I need to do is I have to say fib is the memoized version of fib. I'm not so sure if this is going to be working. Fib. Okay, so let's see. Fib of 100. Oh, wow, it worked. Yeah, definitely. Yeah. So what happened was that fib is now wrapped by the memoize function, and it does this. Okay, wow, wonderful. Okay, so memoization definitely speeds things up. What was I trying to say though? So did I answer your question? Yeah. So if you call fib 36, it doesn't really compute fib 36. It already has, when it computed 100, if you look at this, it actually has to compute all the values before that. So somewhere in the dictionary, it has the value of the FIB36, so it doesn't even compute, it just gives you the value right away. Yeah. Okay. All right, so that's the beauty of pure functions. Okay. Memoization is good. Well, however, if this was the only thing, then like programming languages like Haskell, which is known to be notoriously hard to learn. It's also used by a lot of hedge fund managers, I heard, because they're really smart and they're okay with these things. But Haskell is a type of language that's really pushing functional programming style. You can't program in Haskell the imperative way that we're used to. So you really have to change the way you think. But these languages would have been just purely used for academic purposes, and the computer scientists must have had a real problem trying to convince other people to use things like Haskell or write in functional programming style. But then, you know, multi-core happened. Okay, well, what's a multi-core? In the old days, CPUs were expensive, right? So you had a central processing unit, which is the brain of the computer doing all the computation. You only had one CPU. But nowadays, if you buy one CPU, inside it, it has several cores that can do the work simultaneously, right? So instead of, the biggest problem is Windows. You know, when Windows 3.1 came out in 1980s, the Windows 3.1 came out, and it was people were very interested because instead of having to type things into the terminal, it was graphical. But the problem is the CPUs back then were single core. So to run various programs at the same time, the CPU had to go through every window that's open, do one thing, and then you go to process the next thing and next thing. It was like brutally slow. You couldn't really use it. But then by the time when Windows 95 came out, no, actually, I think even 4086 was single core. So at some point, people began to, the companies began to manufacture dual cores. And dual cores changed a lot. It made these Windows programs run a lot faster because you could have certain windows to be processed by one core, and the other cores can be doing other Windows programs. And now you have like quad core. AMD now has these things called Threadripper, which is like 64 cores, stuff like that. So those computers are much faster, and people working as like computational scientists who have to process lots of data, they realize that they need to have a new kind of programming style because you want many different cores to work on the same data. And the previous way of thinking about algorithms didn't work for the later ones because so in the sorting algorithm that we were talking about, there was like the bubble sort, and you had to compare every one of them to the other. So like the algorithm was like n squared, whereas the quick sort had some nice way of allowing less comparison. So it needed like n times log n comparison, so it was faster. I was trying to demonstrate that. So these are called algorithm complexity, and before dual cores were a thing, people would judge how fast the code runs solely by how many instruction sets were being executed to achieve something, right? But then once you have these dual cores, quad cores, and stuff like that, a big issue was how do you make different cores work on the same problem together? And this is not so easy. So nowadays, if you're working at a company as a data scientist, it's not so strange to be working on like customer data size of millions, right? And if you have millions of customer data size, just doing some small thing could be taking a lot of time. So suppose you have a data size which is like a shoe size in inches, and you want to convert that to centimeters because you need this data to be used in the European market, right? So now what do? You take every inch data, multiply by 2.54, you get a centimeter data, right? But you're doing this for millions and millions of data, and that takes time, okay? So what do you do in that case? Well, that's when functional style comes in. So another big thing about functional programming style are these specialized commands called map, and then filter and reduce. Okay, Python happens to have map and filter as one of the basic commands, and for reduce you have to import it from somewhere else. It used to be in the basic, but then they moved it to somewhere else. So, but let me show you what this does. Okay, so for example, you have a function that define inches to centimeters, which is like you take x and return x times 2.54. Okay, no, 2.54. Okay. Now you have to apply this to a big array of data. So let's say range. Let's just do 1,000. Let's do 100. So this will be a range of numbers from 0 through 100. Now, how do you apply this inches to centimeters to every number from 0 through 100? Well, one way to do it would be the for loop, right? That's kind of the way you're used to do. But another way to do is the map function. We can map the inches to centimeters, in to cm, to the range 100. So in the second part, this has to be some kind of an iterable. You can talk about the first element, next element, and so and so. And this item gets mapped to everything of the data. Now, if you write a code like this, then it's very easy to make it parallel. Parallel means you let multiple cores to do the same thing. So right now, if you do this, this is again an iterable. So to actually execute it, you have to do something like list, convert it to list. So it gives you all the centimeters conversion of these numbers. Okay. So that's what map does, and this is automatically easy to implement as parallel because you can have, let's say you're working with a large server cluster computers where you have like many different computers sharing the same storage space, and then they can grab the data and do something with it, right? So you can have like 10 computers with 4 cores each working on the same data, and doing it to this data would be a breeze. It will be very fast. Okay? So that's map. Right? Okay. Now there's also something called the filter. But just a minute. Before I move on to the next one, let me introduce something. Let me talk about lambda. I wanted to talk about lambda later, but I think I should say it now. Okay, so I can do inches to centimeters as lambda of x and then 2.54 times x. Okay, so I to c of 2 would give me 2.54 times 2. Okay. So Python has this lambda functionality, and this is exactly same as this other function that we made. Okay. So doing this and doing this is the same, and lambda reduces having to define the function separately. So I could have done the code. What was the code? That map thingy. This one, instead of defining the function first and doing it, I could have replaced this by simply lambda x like that. Okay. Now, lambda is another invention of the functional coding style because it's what's known as the anonymous functions. So let's see why that name is important. So look, before we had to define in2cm, and then once you name it, we had to apply that function to all the numbers here, right? But now we're not defining it someplace else. What you're doing is you're just making a function on the spot and applying that function right away, right? Why is this good? Why do you think this is good? First, it's just single line, then multiple lines, right? But what's more is that if you do it this way, then you don't have to name it, right? This function didn't have to have, well, we did name it this way, but we didn't have to have this. This was totally unnecessary. We just we took it without a name and just applied it, okay? So that's a time saver. When you're coding, sometimes making a good name could be a problem because sometimes you want to make a name for this function, but then you realize, oh, I already used that name for something else, okay? That's why it's called an anonymous function. But more importantly, you can just look at this code right away to see what it's doing. It's plainly doing just this. You're just multiplying 2.54 to everything. Yeah. So there's nothing to look for. When you're trying to debug this code, it's a single line, and you can just see plainly all it's doing is 2.54 times x. If you have codes that's like this, you have to think a little bit. Okay, so what is this doing? It's multiplying by 2.54. And where is it being used? Oh, it's used here. Is it used at some other place? You don't know. That's a problem. So you now have to hunt for where it was used. But look, I know that once you do it like this function is never used again. It's just made on the fly and used. You don't reference to that again. So when you chase for bugs, you don't have to worry about this being used some other place. It's a lot better that way. So lambda function is called anonymous functions. It makes the code readability improve. It's a wonderful idea. Okay, so let me use this to do another thing, demonstration with the filter. So what's a filter? Well, filter does this. It gives you a condition. You need to provide a function which will evaluate to either true or false. And then everything that is true is kept. Everything that's not true is thrown away. So let's say you want to get all the odd numbers from 0 through 100. How do you do that? Well, you, again, make a function on the fly. So how do you test if a number is odd or even? You divide it by 2. If this value gives you, this is percent is the remainder after division, right? If you divide by 2 and the remainder is 1, then this is going to be evaluated as true, right? But if you divide this and the remainder is 0, this is going to be evaluated as false, right? So you're going to apply this to a range of numbers from 0 to 101. 0 to 100. This just generates numbers from 0 through 100, right? And then if I do this and then make a list out of it, then it's going to give me all the odd numbers, right? And this is a stupid example, but imagine how this is going to be useful, again, in the big data setting, okay? So, in fact, there are big operating systems out there that's like made specifically for storing big data and processing big data, and those are called like Hadoop and PySpark. And there's a Python library for interacting with Spark, and it's called PySpark. And when you use PySpark, you really have to rely on map, reduce, and filter. And these are kind of commands where you can easily parallelize. You can make several CPUs work together in collaboration. Okay. So now let me show you reduce. And reduce is where it gets more complicated and interesting. The creator of Python decided that it's just too complicated to be in a basic function, so he just moved it to some other place. So now it's in functools. So let's say from functools import reduce. Okay. All right, so let me show you how reduce is done. So suppose you want to have the sum of every number from 0 through 100. Okay, so what you do is you have to define, again, another function, but this time the function should accept two things rather than one. Okay, so for reduce, you always have to feed in a function that takes in two inputs, okay? And it returns x plus y. And then now you apply it to range from 0 through 100. Okay. And then if you do this, then you get a number 5050. Now, in practice, map and filter might not be that hard to parallelize, but reduce is where it gets interesting. If you take large array of numbers and you want to take the average of it, because I mean, if you're a company statistician or a data scientist, like looking at the average value of something or variance of something, all these computations require like squaring something, adding and dividing, doing these operations on very big data. And when you do this, there's something called a race condition. So what's a race condition? So imagine how you're going to implement this sequentially. What you do is you take a total equals to 0, right? Then for I in the list of data, our list is just range from 0 to 100, but let's pretend that it's just some big list here, okay? And what I do is I'm going to take the total and replace the total by total plus this new item, right? And then after this for loop is done, you return the total. Okay, sorry, it's not return, sorry. Print the total. It's not. You print the total, okay? So you would, I've executed total twice. See, that's another problem. Okay, so, all right, so you get the same answer, 5050. But if you're trying to make different CPUs collaborate on this kind of algorithm, it might be that when the person read the value of I and also read the value of total and added, if one CPU computed this and now it's ready to write the value in the total, when it was trying to do that, another CPU did a similar computation and overwrote a different value. So it could have been like the total may have been changed. So if one CPU added +1 and before this other CPU realized that there was a change, it didn't know, and then it just still added another +1, this previous +1 would be erased, right? So there's a big problem when you have multiple things trying to do the same thing this way. So, so it's not so easy once you start doing the reduce to be done collaboratively. Okay, so that's why you need to have some kind of a specialized command for doing this efficiently. And what reduce does is it will it won't keep track of a single total global variable. Instead, what it's going to do is like every computer, every CPU is going to take two pair of numbers and add them, okay, and store them separately. And then once that new list is done, and then you send it to another set of, so you just keep composing these functions over and over and over again. And by doing that, you don't have any race conditions, and you get the answer by allowing several CPUs to do it together. Now, unfortunately, although Python has all of these nice map filter reduce, it's not parallelized by default. So to actually benefit from the power of this multiple processing, you have to do like from something called import multi-processing, and you can do some more stuff with this. There's a separate map command in here, and if you use that one, that's going to use all the CPUs that you have. So that's much more efficient that way. Yeah, but if you're using something like JavaScript, they do have map reduce and all these things that are parallelized, so it will work really fast. Yeah. Okay, so let's just summarize today's lecture. Okay, so I want to say number one, using functions is not functional programming. Okay. Number two, the benefit of functional programming is that you build complicated functions by composing functions, okay, and currying. Okay. Oh, there's one more part that I forgot to say. Okay, I'll demonstrate one last thing. Okay. Three. Okay, another importance is that you want to use pure functions. Okay. So in fact, if you can't use pure functions, you can't claim that your code is functional programming. Okay. To claim that you've written in pure functional programming style, then most of your functions should be pure. Okay. And then number four, pure functions make debugging easier, right? When you find an error, you don't have to worry about a lot of things because you know for sure what it does, okay? Pure functions can be memoized to speed up, okay? Number six, functional programming allows map, reduce, filter to benefit from parallel processing, and more. There's also or other parallel computing style. Like there's something called SIMD, single instruction multiple data. So the modern CPUs, not only they have multiple cores, but even a single core can process multiple data at the same time by using something called SIMD. So instead of adding just two numbers, it can accept like 4 or 8 different numbers at the same time and just do the addition at once. So if you know that what you're trying to do on these data is just adding, then you can do single instruction multiple data type of programming to speed things up by 4 times. Even some people even claim like 40 times faster. So that's another important thing. Another important place is GPUs. You play a lot of video games, right? If you play using a good graphics card, what the graphics card is doing is it's doing a lot of matrix rotations and all these polygon calculations, which is basically linear algebra. And by linear algebra, I mean a lot of multiplication and addition. Many, many multiplications and addition done at the same time. All of these data will be, for example, if you rotate your view from like 30 degrees and everything rotates together, right? So all the things in the screen are subject to the same kind of calculation. So in GPUs, there's something called shaders, which are, in terms of functionality and power, they're much slower and it doesn't have lots of functionality, but what it does is it can collaborate. Like 256 shaders can work together. It would receive a single instruction and all execute the same thing on different types of data. So all of these are very easy to do when your program can be written as map, reduce, or filter. So that's why the functional programming style will be good for this. Okay. Now, lastly, I forgot to mention this, another important part. So there is a concept of programming called DRY, and it's an acronym for Don't Repeat Yourself. Okay. And it's kind of obvious why people want DRY, because if you make an error in one part of the program, or even if it's not an error, if something changed, let's say the database format changed, then you have to change the way you fetch the data. Now you have to go through every place in the code that fetches the data. But if you have copies of the same kind of thing in many different places, that makes your work even more hard. So do not repeat yourself is very important. But think about this. Suppose you have a function defined, print something. Print something, okay, X. Okay, let's say print list. Okay. So you take a list, right, and then you do is like for item in list, print I. Okay, and then the next day the customer says, I need another function that prints only the odd numbers. Okay, so now what do? You take print list odd. And then what you do is if I%2 is 1, then you print I. Right? Okay, so you've made another function, right? And then the next day, the customer comes and says, the customer shows up and says, I want it to be printing only if it's even. So now what happened? You basically have three different functions doing almost the same thing, right? And this is not good, because if somebody changes the way we print, so for example, if you wanted to do a slow print or some other kind of print, then you have to go through all of these three codes and change this line to something else, right? So now, this is definitely going against the DRY principle, right? And to fix this, what you do is you define print list again, and what it's going to do is list, and then what you do is function. You're going to put an optional function, which will determine what the condition for printing. So you're going to do the following. I'll just say lambda x true. So default is that whatever you feed in, it's a function that will give you true as the answer. Okay? And then you say for I in L, if func on I is true, then print I. Now, let's see how you can do this. You can do print list odd can now be just print list, right? with this L, right? But now the function that we're working with would be lambda of x, where x% of 2 would be 1. Okay. Now the problem is this is going to complain because I haven't defined L, right? But that's when something called partial evaluation comes from. So there's another one in function tools, that func tools, that allows partial evaluation. So you can pass on to this function and not evaluate this one and only evaluate this one, and it's going to be partially evaluated, and you end up with a new function. So if you do it like this, then you don't have to change the code. If you want to change the print code, you only have to change the print once. Okay. So this concept of partial evaluation, and this function is called the callback function. The concept where you can plug in functions into a function, that's called the callback function. And callback functions and partial evaluations are also another important part of functional programming, which allows you to avoid avoid having to repeat yourself. Okay, so these are the things that are important concepts, and you don't really have to program in functional style, but a lot of times when you have to refactor your code to make it look more efficient and not repeat, and also make it faster by using parallelism, functional programming style is something to look at. So this was a small lecture on this. Hopefully it was informative. That's all for today.